Okay, I'll come back and pick up anybody's quizzes that are still out. So some of you handed yours in, but if you have not handed yours in, you want to hand it in, I'll take it now. If you didn't get it, if you want to do these period, that's okay too. But I'm going to be talking about chapters 9, 10, and 11 tonight. I'll try to get through, I'll try to do justice to those three chapters. I will not get through chapter 11, but I'll get started on it. So basically tonight, I want to go through quickly 9 and 10, and then just talk briefly about chapter 11, and then we'll finish chapter 11 on Tuesday night, go through a scenario of an old test and give you an example test. What I'll do on Tuesday night is I won't hand you a test. I'll just have it on the video, and then you can look at the video. I'll try to get that posted Tuesday night, and you can look at the video and you can see the questions there. I think it's too much to have to give everybody a copy of the test, but you have the old tests given on the website, so they're there. Just a matter of, you question what my answers might be on some of these or how I would answer some of these questions. I think that's fair. So I want to do that on Tuesday night, and then Thursday night of next week we'll have our midterm test. Any questions? I also, I'm yelling. I also want to give you a heads up that I will be adding more of the higher point labs and give you a lot more of those that you can concentrate on in the second half of the course. But I just haven't had time yet to go through and identify some of those, but I will. And I'll put those on a copy of the syllabus that I'll put on the website, um, hopefully over the break. Okay. So we're going down to chapter 9, and this may be a boring chapter to you. You may not think that you need this chapter. You may think, why would I ever ask to do this, something like this? But yet you do. Every one of you, if you work in the controls industry, you'll have to do chapter 9. It's not an option. You have to do this, okay? And it's a good thing and a bad thing. What you will find is if you work in the controls industry, you will get burned out if all you do is program. If you program daily, every day, every day, every day, you will burn out at it. But if you can go back and forth between doing control programming and other things like this, you will find that your career is much less hard and you can do more, you can enjoy it more. And I think that's a part of anybody's life is they want to enjoy what they're doing and they want to find some purpose in it. So again, I want to just remind you that this is not a bad chapter to at least know some things about. So we first talk about 24 volts and in a factory, and that's extremely important that you think of 110 volts as the used standard, but 24 volts is also becoming more and more prominent in factories. So again, 110, 24. We're going to talk about some of the differences later in this chapter, but I want you to understand that you can have controls at 24 volts, okay? So here is some of the panels that you can buy, some of the types of panels that you can buy, some of the vendors. And you can go all out really nice, or you can just go plain Jane. But anyway, you can have all different types. Now, what you must consider is where you put it what the temperature is where that's going to be, and also the humidity or the other special conditions. I had a panel that was, I didn't build, but I had to start it up in a rendering plant where they were slaughtering cattle, and they used 700 psi water everywhere after the last shift was out. So they every day they sprayed it down with 700 psi water. There was nothing that didn't have a tight lip over seal like this that you could that would withstand that. So in other words, if you didn't have a panel that had a lockdown of that kind of steel over steel lockdown, it would penetrate, and it did. So you could open the panels and water would come out, and that was not a good thing. In in industry, terminal strips are used instead of breadboards. So if you ever think in terms of how you're going to construct a panel, you're going to use terminal strips to land wires. And also, many a time, you're going to have to add things called surge suppressors or bleed off resistors. Now, again, I don't want to get into this in depth, but you can have a situation where an output turning on an input the input will always be on. The simple reason is because most outputs have leakage current in them. If they're solid state, they have leakage current. And some inputs will detect that leakage current and actually turn on with that leakage current. So that bleed off resistor is sometimes necessary in order to alleviate that. Not always, but sometimes. You have to be careful. And also, how you draw panels is extremely important. And this is some of the examples of that. And I'm going through this quickly, I know that, but I want you to understand that you can go back and look at this stuff later on. You also pick a family, okay? You pick a family of I/O, of cards. You don't go for a little from this and a little from this and a little from this and a little from this. You pick a family and you standardize on your job so that you have to minimize the number of spare cards that you might have in a project. Here's families of cards with Allen Bradley. Here's families of cards with Siemens. So you can look at each of these and say, I now know that I don't have to just choose one or the other. And there's a PLC that is behind a screen of a computer. So that's all different kinds of PLCs, okay? Now, when you're wiring AC, you basically are home free because an output is 110, an off is 0. If you're wiring DC, however, it's a different story because an on can be a true high or true low. And if you don't understand this, and if this is something new to you, I'm just going to look at this page right here, page 17, and say, if I ever get in a situation where I'm looking at true high and true low DC inputs and outputs, I'm going to check back with this because it does explain it well. It's which way is the current flowing? All right? When is an on? When do you detect an on and when do you detect an off? Now, we have true high in our panels. Everything is true high, which is like AC. I picked it because it is like AC. If you pick the true low, it is the opposite. But if you ever get into a situation where you are confused about this, refer to this page because it does explain it pretty well. Here's some of the tips about wiring in panels. Typically, you build a panel so that you have wiring space for the wiring that's coming in from the external, from the outside, a terminal strip where the wires are landed, and then an internal wiring strip where you actually bring the wires that are internal to the panel, okay? This is commonly referred to, this wiring channel is commonly referred to as Panduit, P-A-N-D-U-I-T. Panduit is a brand of wiring channel in panels. It's like, give me a Kleenex. It might be a Kleenex, or it might be a Puffs, or it might be a table cat off of your table that you just ate supper at. Anyhow, Panduit is a brand name, but it is a popular brand name for wiring channel in panels. So you can say this is Panduit. No, it may be something else, but the common name for wiring channel is Panduit. Like when you're in the South, it says, give me a Coke, and you say, now what kind of Coke do you want? Do you want a 7-Up or a Dr. Pepper or do you want a Coke? Whatever kind of Coke do you want? So anyway, that's what that is about. Now this is a thought process. And it really is kind of interesting that you've probably never thought about this. Usually when I ask this question, maybe one or two hands are raised that you've ever heard about the tap rule before, okay? The question comes up, when you are working in electricity, you have to protect the wire with a circuit breaker in front of it. So here you come with your circuit breaker, and then you have a wire, right? So if you have a 20 amp carrying wire, in other words, if this can have 20 amps, you must have at least a 14 or a 12 gauge AWG wire. And you would say 20 amps right there, right? Or if you have a smaller gauge wire, you would say this is a 14 AWG or maybe a 16 or a 12 AWG wire. If you have a smaller gauge wire, you would say maybe 1 amp, and that might be a 22 AWG wire or something like that, okay? Smaller wires have to be protected. It's the same as bigger wires have to be protected, or they'll burn up. However, in a control panel, you have what we call the 10-foot and a 25-foot tap rule, which says I can have a big terminal strip here, terminal block. It's a terminal block with places to land wires on, and this is like a 60 amp block. Let's say it's a 60 amp, but it's good for 60 amps. And I can have wires coming off of this and going 10 foot that are real little. I can put a 22 gauge wire off of the 60 amp and go 10 feet. If I go with a 14 gauge wire, which is good for 20 amps, I can go 25 feet. Okay? Now, what is the rule here? It's this called this tap rule. Okay? So if I have a block that's feeding wires, I do not have to provide a circuit breaker for every wire in a control panel if I don't exceed these two rules. 10 foot for any gauge wire, 25 foot for a wire that is rated at a third of the ampacity of the terminal block. Probably never thought of that before, but when you're getting into building of panels, this is a big plus because you don't have to provide circuit breakers for all these little wires, all these little circuits, okay? Another thing that you're going to run into is that of control voltage. In a house, you have three wires. You have a 0 volts, and you have a plus 120, you have a plus 120, and these are 240 out of phase. There's 240 volts between them. Now, you would never put that in a control panel. Why? Because what will an electrician do if he's in the middle of trying to fix a circuit? If your circuit is off of this side, he might pick this one instead of this one, okay? So if you have 240 in your panel, he might pick the opposite side. And if he does, and the relay contact closes, it will weld, those terminals will actually weld together. So you want to not have 240 in your control panel. You want to have 110. You want to have a lot of circuits of 110, but you do not want to have household in a control panel, all right? Again, differences between wiring in a house and wiring in a control panel. Also, every PLC output has a certain load to it, and you need to find what the load of the outputs that you're going to power are. Why? Because you need to size a transformer. And you do not size a transformer based on the maximum load. You size it based on the actual load of the devices you're powering. Okay? Nothing more than V equals IR, but you got to know the I. If you pick the maximum, you'll be picking transformers that are 75 kVA instead of 25 kVA. You say, well, all I have to do is look at what everybody else did and I'll do the same thing. Does not work. You have to pick a transformer sized to your power load. Okay? I'm sorry, but you must. You must say, I need a 25, or I need a 10, or I need a 50, or whatever. but you pick the size that you actually need. You have to do that. Relays are something that you probably will, now that you know how to use them, you'll probably think, oh, that's nice. Relays are really nice. They're not nice. They have a limited number of operations, like 1,000,000 operations, which you say, well, it'll never happen. It does. And also, when they fail, they can fail at the most difficult times, and they're not as reliable as solid state. So if you ask, if you were to pick a relay, what type of relay would you pick? I'll say, I will always try to pick a solid state relay over a mechanical contact relay. Even though now that you know about relays, you think, well, I like them because I can see that little thing going on inside of them, and I understand them. Don't be infatuated with relays, okay? Do not use them unless you absolutely have to. Use solid state. Also, in almost all cases, try to use standard components as opposed to breadboards. If you like to breadboard things, if you're electrical, you like to prove that you can do a breadboard. I understand that. But please do not try to do that. If you do, what will happen? If there's a breadboard in a panel, it'll always be what's wrong. In other words, if an electrician comes along and is trying to troubleshoot it, he'll always point to that breadboard and say, that breadboard is the problem. He doesn't care. He'll say, you got to get rid of it. You got out of here. I don't understand it. It's not something that I can use. If it's a true breadboard, it'll those contacts of those wires will vibrate out. Don't use make it a soldered breadboard. If you're going to make a breadboard, make it soldered. But on the other hand, don't do it unless you absolutely have to. Buy a standard component, and there are a lot of standardized components that you probably have no idea that are out there. But in my opinion, these two companies are ones of the best, Phoenix Contact and Red Lion. So as you are checking out how to do things, these are not bad places to start. Okay? And I'm not trying to advertise for these guys, but they are pretty good. Also, how do you draw the drawings? Well, you can use AutoCAD or you can use AutoCAD Electrical, all right? Now, I'm going to give you a plug here. If you're a graduate of the University of Toledo, you should take pride in some of the people who have gone before you. And one of those is Nate Holt. He lives here in Toledo, Ohio. He's a 1972 graduate in electrical engineering, University of Toledo, and he by himself wrote AutoCAD Electrical. The original AutoCAD Electrical, he wrote by himself. All right? Yeah, he did it 80 hours a week for months on end, but he did it, and then he sold it. He made a lot of money. The guy's pretty rich. But I'll tell you, he's a good guy. He's a smart guy. He's a good guy. Very dedicated, but he wrote AutoCAD Electrical. The first round of AutoCAD Electrical was totally written by a University of Toledo graduate. All right? So take pride. It's real. It's a real guy, and he did a really good job. Now it's been taken over by AutoCAD, and they've rewritten everything, and I know it's this and that and whatever. They've now own it, but he owned it before they owned it, and he did a good job. Okay? And there's how it works. So you can make drawings that you can go out to vendors with, and there's some catalog cuts of how the thing works, and that's how it works. There's examples of how AutoCAD Electrical can create. Now, AutoCAD Electrical is not, it does not troubleshoot your circuit for you. All it does is it builds what you design. It'll get it built, is all it'll do. It'll get it built. You have to then troubleshoot it yourself. It is not a simulation package like Multisim. It is not a simulation package. Okay, now every city or every area in this country has an AHJ. I never knew what the AHJ was or who they were. Authority having jurisdiction, but there is one. For every part of this country, there is somebody, and they determine the rules as how components are to be used and how you're to put panels together. They usually follow the National Electric Code, and they're 1 to 2 versions later. They're delayed. in the National Electric Code, but usually they will interpret that. Usually you don't have to worry about them. They're they're out there someplace, but unless you have an industrial accident, you never see them. There is a part of this that is something that you should pay attention to, and this has to do with SCCR. The SCCR stands for the short circuit current rating of a panel. Okay, so each panel that is built has to have a label on it with a SCCR, the short circuit current rating. So when you walk up to a panel and if it doesn't have this tag on it that says SCCR, you're not to open it. You're not supposed to. Now that puts you in a dilemma because if you're in a company and the person tells you to go up and open that panel, what are you going to do? Well, you can remind them that the panel should have a short circuit current rating tag on it, and it should. If it doesn't, I don't know what you do. I'm not going to tell you to open the panel. Why? Because they've not followed the law. The law says now that you must have this panel on each panel that you put out, okay? Now you say, what happens if you don't? I don't know. But you might end up, if you open that panel, that you might open up with having to wear a suit like this. This is the worst case. There's 4 levels of severity. Level 1, level 2, level 3, and level 4. This is level 4. This is the worst case. Now, why would you have to wear something like this? If there is an explosion like that in the panel, you can get killed. Simple. It is not an electrocution. It is a spray of copper, and it will kill. If you just dial up arc flash, that's called an arc flash. If you just dial up arc flash on the YouTube videos, you'll find some of the goriest pictures you'll ever imagine. And I'm playing with the idea that I'm going to require you over the holiday or over the break to watch a 1-hour video. I'm not sure I'm going to do it or not, but it's a video that I have that was taken of a guy talking about arc flash here at the university. And it's a very potent video. 2 guys get killed in it. You can see them getting killed, and it's not fun. But they also talk about electrocution in that video, and again, it's not fun. But that's called arc flash, and it's dangerous, and it can happen, all right? It can happen. So again, I don't want to scare you. I don't want to make your life miserable, but this is a possibility. Be careful. And again, the panel should have this rating on it. You should be trained. You should have certification before you open a panel. Now again, there are panels that are 24 volts that don't have any rating. Anything less than 50 volts, guaranteed, anything less than 50 volts doesn't have, there's no rating, okay? So you can walk in and not worry about it. The 110 volt panels, it's a level 1 rating and they're not bad, but you get up to 480 volts and high current ratings and you can get this. And you're going to have to wear that suit. And you say, well, I'll get hot in that. They air condition them, okay? Anyway, the video is explaining a lot more than I possibly can, and also how to, if you're an electrical person designing a panel, if you're a person, whoever, mechanical or electrical designing a panel, I have in my other course, and I'm going to show you right here where it's at. It's in this course right here. It's in the one with, so I have to teach this, right? I have to teach the rules because I'm an electrical person, right? By the way, when I was doing this stuff, we didn't pay any attention to this. And the last time I did a consulting job was 2010, and that was right when they were starting, and they had these little stickers on panels that says danger, high voltage. I said, these are 110 volt panels, they're not high voltage, and I was taking the stickers off. That's how naive I was, how dumb I was. So again, courses under my auspices, 4350 right here, electric power systems. And this has to do with well, I call my supplemental text, which was my panic mode of taking that course last semester and actually trying to teach it. But I found that there is a company called Eaton, EATON, that does a really good job of talking about short circuit current rating and how to get at it. And it's in this 266 page copied text that I basically made up out of all the stuff that I could find. It's in there how to do that. So again, I do cover it under my text. It's not my text, it's a copied text, it's a plagiarized text, but it's there. How to find the short circuit current rating. And there's several really good videos that go along with it that help it as well. So again, if you're confused about short circuit current rating and what that means, and the fact that, oh, I'm building a panel, but I've never heard of short circuit current rating, you need to bone up on it before you put a panel out the door. If you're in that mode that you're doing this, and you're working for somebody that just basically hasn't read the rules in the last 15 years, the rules changed. In 08, they changed dramatically. Okay. There's another picture of what you don't want to have happen. That's more copper sprayed out than you can imagine. And it will kill. Okay. So the three places you need to look for rules. Okay, so how do you find out about this stuff? Well, obviously I just told you, you look under the YouTube videos under Eaton, and they're there under short circuit current rating. But the three places the rules exist are the NEC, National Electric Code, NFPA 79E, and UL 508A. There they are. Those are the three places that these are covered. This covers all of your wiring in your panel and outside the panel. This covers the rules for when you can, what constitutes having to suit up, and this constitutes how you put that tag or that label on a panel. What that label must say, and how to configure the tape, how to configure the plate that goes on the panel that basically tells you how it works. So those three, National Electric Code, latest one, NFPA 79E, and UL 508A. So that gives you an idea of where to look. Now you know some buzzwords that you didn't know before. Maybe you knew all this stuff, and maybe you don't care. But if you do care, and if you're going to work in it, you should know the rules. Okay. Now, here's another thought. How about no panels at all? Maybe you've never thought of this, but they do have a way. The Germans do, and I don't think it's caught on the United States yet as much. But go without panels and just basically buy the components and put them on the wall, and then couple them together with plug cords. Okay, you can do that. It's doable. Here is the ideal panel that must have that rating. This is a panel with motor starters in it, 460 volt. It's loaded with 460 volt, and you must have that label on a panel like this. You must have it on every panel, but this is one that it's not going to be level 0. It's going to be level 2 or level 3, or maybe level 4. Okay, moving on. Now this is moving outside of the panel and every other area that you want to have electricity and how you deal with that. So we do talk a little bit about sensors, and you have some sensors on some of the things that we have in the labs. We do have some devices. We don't have a lot, but we do have some. But you will deal with sensors a lot. And by the way, every circuit, when you commission a system, Every circuit must be checked out. You cannot walk away and say, I'm ready to go, unless you have checked out every possible sensor and say it's working and it's working the right way. Unless you've done that, you've not checked out a system. Okay? Hopefully, you get that through, because if you don't check the system out thoroughly, what will happen? After you said, let's start up, you'll have me started up, and then you'll be going back and checking it for real when you're actually trying to run the system, and that's really painful. That's not the time you want to check things out. You want to check things out and then start the system up and have it thoroughly checked out and be confident that the switches work the right way and that they're working. And that's why they pay you a lot of money, because I know you're going to do that. Please do not take shortcuts in not checking out completely every system. I honestly, I did not think about this as I was starting to work in industry. I thought if I could take a shortcut here or there, nobody's ever going to figure it out. I'll be okay. Everything's going to be fine. And I had a friend that helped me on one of the first projects I started up at Owens Corning Fiberglass. And after I had been with him for a week, he was there with me for a week. And on the day that I took him back to the airport and let him off, he said, Ted, I think I left a little piece of wood under a contact on one of the motor starters in the motor control center. He said, I think I left it there. I was checking to see that the normally closed state of that contact. And he said, I think I left it. And I went back and there it was. But he was so thorough. Everything that he checked out, it ran. And honestly, I got it. From that point on, I did not ever take any shortcuts. And again, I don't want to impress you with I was so good. I'm not. But that impressed me a lot, that you have to be thorough, but when you have a chance, so that when you start a system up and it's ready to go, that you don't have to worry about, well, is that circuit going to work? I didn't really check that one out. That's not a good way to go, okay? Okay, so now I'm going to talk about different types of technologies. This is a photo eye. You will use a lot of photo eyes, a lot of them. And you know them because that's what's in the garage at your home. It's across the base from one side to the other, and if you walk into it, if the garage door is coming down, it'll go back up. Okay? Now these are not visual. These are invisible. They're infrared. Most of them are, and they're not constant. They're a pulsed LED, so they've got it's a pulsed signal. Okay, they do not respond to the sunlight. They only respond to the pulse that's being sent by the transmitter. So you have a transmitter, you have a receiver, and that's the only thing they respond to. Hang on, I got to get this thing. I'll be right back. Sorry. Hello? It is, yes. No, back would be fine. Good, yeah, that's okay. Well, the doctor, thank you. Appreciate it very much. Thanks. Sorry about that. Sorry. Okay, it's a pulse signal. It is not a constant signal. The transmitter gives a pulse signal, and the receiver only is trained to receive that pulse signal. Light from any other source will not trip it. However, from another LED, from another transmitter, you can get a bad signal. So, and these spray out like this. So if you have one that's here and then one that's down here, they can crosstalk. All right. So what you typically do is you put one on one side and one on the other. So you go back and forth like that. but they can crosstalk, and you must be aware of that. All right? A lot of modes, a lot of different modes. I don't have time to go through all of those tonight, but please, if you get into photoelectrics, it can be a whole side area that you can study, and it's a extremely good area to be knowledgeable in. This is a proximity switch. A proximity switch is it detects presence of metal, and it detects the presence of metal up close, usually about to a third of the diameter of the head. So a bigger head can go further, a smaller head can go less far, but it detects metal to the distance of about a third of the diameter. Okay, this is a camera that is programmable, and they're extremely intelligent. You can program these things to do almost any kind of part source sorting, bad part detection, all that kind of thing. And we have some of these in our area. And I will conclude this as a lab. If anybody wants to do this, I'll include this as a lab. This is a Cognix camera, and I have plenty of these for you to try. RFID versus barcodes. RFID is radio frequency identification, and these are RFID read-write tags. We have some of these in our lab as well, and we have the programming of them and the ability to program these. Now, where are these used? Anytime you have a moving part, you can have this, and basically it's a floating database. You can read from it, where has that part been and what has it done. In other words, this is an engine, the block of an engine that you're moving down the line, and it's this hole, this hole, this hole have been drilled, we're ready for this hole. And that can be programmed into that RFID tag, which floats along on that engine block. So this is a way of controlling how a device how you move through a system. It's a way of tracking progress through a system. Okay. Okay, this is the machine directive, and it has to do with this has to do with what I talked about before about making sure that whatever you program is safe. And there's a picture of a disaster. Okay, yes, you can have bad things. NFPA 79 talks about safety standards for machine control. NFPA 79E talks about arc flash. Risk assessment we talk about more in chapter 20 than here, but there's a subject of risk assessment. What is functional safety? Okay, there's two types. One type is the type that will cut off an arm, a leg, or that type of thing. It will puncture you, kill you based on the fact that it will ram into you, or it will cut you, or that type of thing. That's a moving part type device. A fault tolerant one is one that will blow up. Okay, like the fertilizer factories that keep blowing up in this country, and that's that type. Now they both have to do with safety, and they both have to do with you have to provide safety in both cases. All right, it's a different type of safety, but it's safety. So this is called fail-safe. This is called fault tolerant. Okay, and there's a risk assessment flowchart. Now, how do you make something safe? Well, in the United States, you basically do what somebody else did, and you put a bunch of safety guards on it, that type of thing. In Europe, in Germany, there's an insurance directive that is basically in charge of making things safe. So you dial them up, and they are the people that tell you how to make a machine safe. And they've got a directive for about every kind of machine there is. So if you type in BGIA, now that has been changed to BGIA is now something else. But anyway, ISO 13849. If you dial up BGIA, you're going to find them, okay? And it'll tell you how to build a system safe. I have to add a little humor. I'm sorry. But anyway, it's like take it or leave it, right? It's not everywhere, and you don't find it very often, but it's just there a little bit every once in a while. This is intrinsic safety. Now, intrinsic safety has to do with things that'll blow up, okay? Things that can go boom. So you have to provide arc flash, not arc flash, but arcing safety from that happening. So anytime there's a possibility that a spark will cause an explosion, you have to guarantee that it won't happen. So that happens in grain, it happens in petroleum, it happens in other kinds of places. And how do you find out how to control that? Well, you read the National Electric Code, section 500, 501, and 502. How do I know so much about 500, 501, and 502? I built a few projects that had to do with 500, 501, and 502. I got to know them very, 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 very well. Okay? And they're NFPA parts that had to do with that as well. But National Electric Code 500, 501, and 502 nails how you handle intrinsic safety. Burner management is a whole separate subject by itself, and it's governed by these rules. Okay. Now, analog signals are also covered in this chapter, and I'm going to give you just a few examples, but basically we have a lab that I've asked to move from its present location down to 1100. I haven't done it yet, but I will. We'll get it done. And it has to do with the bicycle, okay? So if you like to get your exercise and you like to get credit for a 4-point lab, join the bicycle group. But basically what it is a bicycle that allows you to pump it and expend energy, okay? And you program it. Put a program together that shows the calories used, and you will get 4 points. Diagnostics. I'm not big on diagnostics because why? When you need them, you will use them and you'll find out about them. But there's a lot of diagnostics tools in the PLCs that you'll find that are very helpful. In other words, there are things that you can look up that will show you things about the processor and what it's doing. Diagnostic tools. They're there. Okay, any questions about chapter 10? What is this? It's a permissive string. What is this? It's which one of them was the culprit? Which one of them was the bad boy? And this is called a first out detector. So anyway, diagnostics. There's a lot of okay, really there's 3 areas that you program. One is control, one is the HMI, what the operator sees, and one is diagnostics. Now, your best programming techniques will take into account all 3 of them at the same time. In other words, if I make a change, did I make the change just in the control area, or did I also include the diagnostics and the HMI part as well? So you're always having to ask that question. Did I take care of the control aspect of what I did? Did I take care of the diagnostics aspect of it? Because I guarantee if you make a change over here, you better make a change over here to make sure that your diagnostics program that was working on this program, it didn't get messed up. And also the HMI. So again, please realize that you're going to have to do all 3, and they should be coordinated together. Any questions about that? Other stuff. And the watch table. This is where you watch how things work in Siemens. Alan Bradley has a data table, and they now have a watch table as well. Okay, again, not a big part of it, but it's there. Okay, so now let's go on to chapter 11. This is by the way, chapter 11 is the most heavily trafficked chapter in my book, and it's been that way for a long time, except now that people are doing the Rubik's Cube, some of the Rubik's Cube projects are taking over the highest spot. But this is the chapter that nobody else seems to have written, or if they did, they didn't do a very good job, because people read this, and I don't know who's reading it. I don't really care who's reading it, but evidently there's enough people who read this that it keeps getting heavily trafficked. So this is, and heavy is not like I'm not making any money off of this YouTube channel, and I don't really care. But this is the one chapter that by far is the most heavily trafficked of people reading my stuff. Okay. Now, what's important in this chapter? Okay. When to use state tables is the most important concept in this chapter. When, okay? State tables by themselves are not that big of a deal, but they can be important and they can be very useful. Now, one of the things you can do is you can say, when you see what that is, what is that? That's a cylinder, okay? What's its purpose? What's the purpose of a pneumatic? That's a pneumatic cylinder, by the way. You can have hydraulic cylinders, you can have air-driven cylinders, but you can, or no, you can have electric motor-driven cylinders. What's the purpose of a cylinder of this kind? Hmm? To control movement, right? You move back and forth, right? Anytime you have a cylinder, you have a high potential for a state diagram. All right. So if you're looking for when do you use state diagrams, that's a good tip off. All right. I'm going to tell you a story. Again, this is a hero story. Some of my stories are not hero stories, but this is one that is. So basically, one summer, I was basically waiting for school to start, but there was about 3 weeks, 2 weeks, whatever left. And I called one of my friends in LOF and I said, you guys have any little projects that are still outstanding that you don't have anybody working on that you need some help with? And the guy said, nah, I don't think of anything, kind of laughed. We just kind of joked, and that was the end of that conversation. Later that day, he called me and he said, you wouldn't believe this, but he said, we might be able to use you. Oh, okay. What's this about? Well, in Shelbyville, Indiana, they had a fabrication plant. All right. This story has many aspects to it, and I hope I don't mess it up. But anyway, the one thing about it was this fabrication plant, they made automotive glass, but they had to cut it to shape, and then they put it in an oven to heat it up, and then they bend it. So basically, it was a two-step process. You cut it to shape, then you put it in and bend. Okay. So the part that was cut to shape, that part, the line had been down for a while. They had taken it down and they'd redone everything, and then they put it back in operation. The problem was that the main line, there were about 4 lines, but the main line on this one, the fellow that was in charge of doing the upgrades had not made the proper change. Okay. Now the change was these are pieces of glass, okay? And there was a station here, and then there was a station down here, okay? Now the time to travel between that is fairly long. Believe it or not, travel of a line takes time. And this was the bottleneck. So if they could put a piece in here and then travel from here to here, and then from here to here, they cut the travel time in half, which took out that as a bottleneck. So basically, they were trying to increase the overall speed of the line by eliminating bottleneck. And that's all they were trying to do. This guy, they had given him a period of time to try it out and all that kind of stuff, and he had not gotten it working. They had to restart the line because they had to get production going again, and it wasn't working. It was not going at this with this new approach. So he had tried, couldn't do it, got frustrated, put his hand through a computer, and he walked out, and that was the end of that guy's career with LOF. Bad news, and I'll tell you why, because in Toledo, Ohio, they do still, I think, have a box that you can check when somebody leaves a company that says, would you rehire this person? And guess what? If that box is not checked, it's hard to get a job in this area. Now, if you move to California, they don't care, you're fine. But if you want to get another job in Ohio, they may check that little box to see if that was checked or not. And if it's not so easy. So anyway, I don't know if he's got that box checked or not. I don't really care. I'm sorry for the guy. He was frustrated, put his hand through the computer, and that was the end of that. But 2 other guys had come in, and they had tried to get this thing to work, and they said they blitzed it for a day or 2. They couldn't get it. So now what are they going to do? So they said, here, Ted, you see if you can do it. Well, I had an advantage because I knew the guy who had programmed the original line. Okay, now he was smart, and I'm not saying that only smart people can do this, and that's not my point at all. But he was. He was very well organized. When I first moved to Toledo, Ohio, I worked for Libby on Sport for 4 years, and I worked with this guy for the first year, and I saw him in action, and he was way above everybody else in his ability to keep track of everything. And all he did was build state diagram programs. That's all he did. But he was very good at it. Okay? His name was George Bukovinski. He was from Hungary. And in 1956, what happened in Hungary? They had a revolution. George was on the wrong side. He was on the right side, but he had to leave. He had a price on his head. He got out. He eventually got his family out. He came to Toledo, Ohio, and he had been studying to be a doctor, but he was not a doctor yet. But what do you do in Toledo, Ohio, if you've got about 3/4 of the way toward being a doctor, medical doctor, from Hungary to the United States? You start over. And he started in electrical engineering, University of Toledo. So he got a degree in electrical engineering, University of Toledo. Then he started working for Libby Ford Company. Smart, yes, very good. George Bukovinski was very good. But I had the inkling, how's that this was one of George's programs. And I knew he was very well organized. All right? So what do you do in a case like that? Well, if you look at this as state to state to state, if you can get a piece in here, then it will automatically do this. If you can just get that piece there to start out with, okay, then it'll take off and run. And guess what? It did. So what's the process of doing that? When you first start your program up, the first time you run the piece from here to here, and from that point on, this will go to here, this will go to here, and it ran. Okay? Now I found that in a day. All right? It took me most of a day, but I figured that out in a day. What else did I do? Besides the fact that I looked at it and I thought, this kind of looks like George, and it very well organized, a very, very nice program. What else did I do? That evening, I went over to the electricians and I asked them, I said, does this ever happen that you can actually see this happening, where it gets a piece in there and then it keeps going like that? He says, oh yeah, it happens all the time. That poor engineer whatever. The answer was that far away from him. So the next morning, they came in and they were going to have a big production meeting. The production meeting was only to tell me that I couldn't run glass because I had broken too much glass the day before. Okay, I had caused them production mess ups because I'd broken some glass. Yeah, I had done that. Granted, I'd just been there one day, but I had done that. So they were talking about everything else, and all of a sudden they talk about, we can't break any glass today. And everybody got real quiet. I said, I think I got it. Then they really got quiet. So anyway, long story short, I really blew that job because why? I could have asked for $20,000 or $30,000 for that job, but I asked for $35 an hour, and I had 2 days out of it. I got a couple $100, so be it. It kind of put them back on their heels because the first day that I was there, the afternoon I first came in, they said, those who can do, those who can't teach. Yeah, I've heard that before. Yeah, I've heard it. Yep. Anyway, so that's it. That's the story. But what's my story? If somebody does a good job of putting a state table together, you can add to it, you can modify it, and you can do all kinds of stuff with it. Does everybody understand what I just said, kind of? Anyway, if you organize a state table, if you organize states well, you can do a good, they're easy to modify. And that one was. Okay, so again, that's that. Now, I've got another one for you. This is a little bit more difficult but does everybody see what I did? Very little. But I just initialized it to get the piece in there, and that was it, and it worked. Okay, now another one. Now we're going to come back and we're going to talk a little bit more, but I want to talk about another war story, and then I'll be done. But this is another one, and this is a story from one of my last consulting jobs was this one, and I I want you to understand that they're not always easy to see. Okay, but this is a steel plant, and this is the actual how I did this one in Auburn, New York. Now, I'm not giving away company secrets because I'm not telling you exactly how I did it, but I'm telling the generalities of what I did. Okay? So, this job had to do with bringing steel into a plant, into a reheat furnace. So, basically, this project had to do with okay, this would be a furnace, a big long furnace, and that's looking down from, I'm doing the look down from above. So they brought the pieces of steel in and they laid them here, and these are billets. They're like Lincoln logs, 20-foot long, 5 inch on a 5 inch square or 6 inch on a side. So it's big long piece of steel. It's been a poured piece of steel, and then it's let cool. And now what they're doing is they're reheating it because down at this end of the heat, it's going to be red hot when they get down to here, and they're going to pull them out and they're going to make something out of them. They make channel steel. They make, it's like a taffy pull. So when you get steel really hot, what it does is it's expandable, right? What they were making out of these billets was rebar. No lie, it was rebar, which is about that thick. Rebar is not big stuff, but they were taking that 6 by 6 inch piece and pulling it down to rebar. So that's a lot of taffy pull out this end, and I had nothing to do with the taffy pull. I never had anything to do with that at all. But I had the part right. I wrote the program for the controlling of the heat. In other words, getting it hot, and also the program for getting these billets into the furnace. Okay, so you're pushing them in with a big cylinder. You're getting them onto this table, and you're moving over here, and then you're getting them out on this end, and they're stacked end to end. They're just like this on a big rail. There's a rail under here and a rail under here, and that's all they do. This was a massive cylinder that pushed these because it had to push all of them on this rail. Massive. And this was a long furnace. This wasn't the length of this room. This was about twice the length of this room this furnace was. It was big. Okay, it wasn't so wide, but it was about half the width of this room, about the height of this room, and it was long. Anyway, big furnace. That was how it was done. Now, what I want you to see is I saw this as 3 interlocking tables. In other words, 3 interlocking sets of loops. So the first one they dropped it onto this charge table, onto this table, into the transfer table, and then they moved it over to the charge table. So you can't move a part until you are ready over here. Everybody see that? You can't move from here to here unless you're empty over here, right? So if you look at it in that regard, now you say, well, when do you push? Well, you can't push until one has been taken out. That makes sense? So I built something like this. And this step by step by step. You go step 1, step 2, step 3, step 4, step 5, step 6, then back to step 1. So each one of these steps has a number assigned to it, and that's all I did was a step number. And then when you're at this step and when you're at this step, then you can do a transfer. And that's not exactly it, but it's approximately what they did. Now, what I did was I designed this and I gave them this piece of paper and I gave them the program basically, but it was not complete. But I thought I was going to have to go back and help get this thing started up. And the engineer that was there, I called him after I'd been back from, by the way, what did I do it's over spring break that year? That was 06. It was 05. It was 21 years ago. 21 years ago to this weekend or next weekend. What did I do 21 years ago this weekend? I was in Auburn, New York, starting this system up. Okay. So I got the heat part of it working, and this was the part that was left, and I hadn't gotten it started up, and they weren't ready for it yet. But I called the guy and I said, how are you doing with that? He says, it's up and running. I about fell off my chair. Why was he able to get it up and running so quickly? Because of this way this state table was set up. okay? If you set up state tables correctly, you can interleave them, and you can make a lot of things make a lot of sense with these pictures, and that's all he did, and it worked. I fell off. I said, "You're kidding me." He said, "Nope, it all works. Those numbers worked, and those steps worked," and he said it was no problem. Honest to goodness, I could not believe it, but I did, and that's good. Now, the hard part is seeing when you need these and how to put them in. What was the big tip off? Cylinders and interleaving, because you can't do something until something else happens. Okay? Now, is this the only way this could have been? No, I could have had this step going over here or whatever, but it basically is a step-by-step interleaving of state tables is what it boils down to. Many times, this is how you control a process. You can't put something in until you take something out. Well, you had to take something out before you could put something in. And you can only put something in at this step this is the output side. Everybody see that? This is the extraction part. This is the part that's running down here. This is the one that's taking the part out. This is the part that's charging in, and this is the part that's on that first table. First table, second table, extraction. And they all work together. And it works. I'm not saying but seeing it and then putting it together is the key. And it's because many times it's with cylinders. Any questions about that? So what I've said to you is basically this. State tables have a place, and it's a big part of how you design systems. Sometimes you use state tables, sometimes you don't. It's knowing when to use them, and especially they're useful if you have cylinders. And I've got some of the German stuff here. I'm going to go back and show it to you. The German stuff, by the way, is the stuff that's colored in yellow. This is the German stuff. Now, the German approach is to say, we will control systems, and they do this. They'll say, we'll control systems by giving you state tables of each cylinder independently. These work if you put these two state tables, and if you do this, you can actually get a system to work to have that state table, this state table. You can make a system work. However, this one up here is the way I did it, and this is called a runoff table. This and these two are equal. The runoff table is the way I designed it, and it's the way I believe strongly that you will probably end up designing systems. But they taught this as this is the first approach because you can see the cylinders and you can say, how many states does a cylinder have? 4 states usually, 4 states. What are the states? It's either this way or it's this way, or traveling from here to here or traveling from here to here. 4 states. But that said, this is, I think, inferior to that because that's the way the process works. Okay. Now, another thing about tables and state tables and getting things back is that there's more than one state table. There is the automatic table, there is the manual table, and there is the homing table. There's 3 sets of tables. The homing table is what? It got messed up. We don't know where it's at, but we want to get it back to its home state. That's that table. The automatic table is the one that you want to run with. The manual table is the one that allows you to basically not crash into something, not do something bad, but allow any operation that the person wants to do within reason. In other words, I don't want you to smash something by grabbing hold of a button and pushing a button. I don't want you to smash something. But with that said, you can do about anything you want to do in manual. So there's 3 tables, but usually we only design the auto table well, and the rest of them kind of heck with it. But again, sometimes homing is just, you'll go, everybody just goes home. But sometimes you get into these crash tables where you can crash and make a mess, and you have to put a homing table in order to get it to work to go back. Okay, so that gives you a little bit of an idea of the type of tables that you can have. Will he ask a homing, or not a homing, but will he ask a state table on the test? I don't know. It's simple, it'll be simple, but it can happen, okay? That's not a threat. We'll talk about them on Monday night, but that's what I wanted to get to tonight, was this idea of state tables, and they can be used, they don't have to be used. And I know some of you have had all kinds of automatic development of state tables using set reset, flip-flops and all that kind of stuff. I'm not talking about that kind of a state table. I'm talking about a state table that will allow you to run a process. Pictorials that allow you to run a process. If you understand the state table, you can see how the process is supposed to work. Now, you don't program that, you just program from that. Okay? You just look at that and you write your program. Usually you write with a number. Step 1, step 2, step 3, step 4, step 5, step 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. You go around in a circle. Many times that's how you do it. But it's not always that way. And sometimes you'll see some other state tables that I've got here that don't always just go around in a circle, but most of them do. I know I blitzed through too much in little time, but hopefully some of that's sunk in, and hopefully it will sink in. If you ever get into a situation where you're programming and you say, cylinders, what did he say about cylinders? Oh yeah, chapter 11. Oh yeah, state tables. Should I consider state tables? That's cylinders start the process. If you see pneumatic or hydraulic cylinders in the process, then you start thinking more and more about state tables. Any questions anybody has? Take care. See you.